All right, hi everyone, welcome to chapter 2. This is going to be the lecture video. There's going to be a separate video where I go over the math and how you can do some calculations for this chapter, as well as show you how to perform work in Excel as it relates to these calculations. For this video, we're going to be talking about the math a little bit, but not really demonstrating the math so much. We'll also be just talking about the chapter in general. I may flip through some of the slides a little quicker. I will have the entire PowerPoint with all of the slides that I've removed from this lecture inserted back in if you find it easier to follow along with the PowerPoint on your own as you're watching the video or as you're studying. So that will be available to you. And like I said, there will be a separate video where I go over the quantitative elements. So this chapter is on descriptive statistics. This is going to be a bit of a review chapter. For those of you who have not taken business statistics for a few semesters, and you might have forgotten some of this stuff, and especially if you haven't taken quant or operations management yet, some of these calculations you might not have seen for a while. I realize that students get very anxious on occasion when it comes to a combination of numbers and Greek letters. So I will try to do a very thorough job of explaining the why behind the math, as well as give you multiple ways of solving a problem and just to help further your understanding and kind of alleviate some of that anxiety. For those of you who don't know me, I did tutor here at NSU for a number of years as I was in grad school here. So I have a pretty good grasp on where students tend to get tripped up in these types of classes and try to address that head on as we go into it. So without further ado, here is chapter 12 on descriptive statistics. So brief overview, we're going to be going over some terms, definitions, and I do want to say that this lecture will not be all-inclusive. You do need to study your chapter as you prepare for the quiz and eventually for the exams. You'll need to study the chapter to go over the calculations for your quantitative work, for the problem sets as well. But I try to give enough of an overview to get you started and focused in on the key areas. So terms here, you'll need to know data. So this is all of the facts and figures that you have gathered. This is going to be a large pool or table of information, or rather not information, right? Because it's the transforming of data into information that makes it usable. The data on its own doesn't mean anything to us. Once we analyze it and summarize it, then we can interpret it. Variable is any kind of characteristic that might be of interest to us. The variable could be something like the temperature or the number of sales or the number of units of demand, the student's height or age or something like that. Those are all potential variables that might be of use for whatever our study is, whatever we're trying to, whatever bit of information we're trying to glean. Observation specifically refers to not just the idea of looking at something. You might think of observation as, okay, I'm observing something, but an observation is going to be all of the specific instances of one observation in a set. So an observation would be like this student's favorite color is blue, and they are 15, and they are 5'7" or however many inches tall, and they live in this neighborhood or whatever, whatever potential data you're gathering, right? That's one observation. And then each of those are listed as a separate observation in a set. So you end up with this letter. Often you'll see the letter N used in calculations, especially in formulas, and N always refers to the number of observations. So if you are taking the average of 100, the data from 100 students, you have 100 observations in that set. Variation is going to be when you have measurements or data accumulated that has variability into it. It's a specific measure. There's a specific calculation for variance over those observations. A random variable or uncertain variable. This would be anything where the value would not be known with certainty. Sometimes these are used in conjunction with continuous variables, where it could be any specific number as opposed to exactly maybe an option between 3 or 4 choices. But anytime the value is not known with certainty, we can use an uncertain or random variable. Here's an example of a sheet of data. You have companies, their symbol on stock market, industry, all of those are categorical. Those are just, those aren't used to perform calculations on. But then we have the share price and the volume of shares sold. So all of these companies would be observations. And then, any of these off to the side here would be the potential variables. Share price is a variable, volume is a variable. There could be more things gathered on there. All right, types of data. So here's some terms on types of data. Population would be everything. Population would be all students in a school, right? Or all students in 8th grade, right? A sample would be a subset of the population. So if we wanted to find information about a population, typically what we do is we do random sampling. We pool maybe 100 respondents, and they are used to sort of not predict, but just to represent the likelihood that the entire population falls under those same variables, under the same observations as you spread it out over a larger percentage of people. This is done with TV ratings. If you're a Nielsen family from back in the day, and I know they still keep doing it, but you would fill out a thing of paperwork every week or of all the shows you watched, and they would say, okay, well, I have 1 million people turning these in. I know we have however many, hundreds of million people in the US, but we have 1 million people turn these in, and this is the percentage of people who watch this show. And then we spread that out over the population of the US and kind of predict that there were, or use an estimation that there were this many people that watched this show. That's how they would get ratings for how many people are watching stuff. So you random sample, and then you expect that percentage would follow the same pattern over the entire population. Quantitative data is anything you can do math to, right? If I asked a bunch of students, a bunch of people, what their favorite number was, okay, and some people said 12 and some people said 7, that is going to be categorical data. That's not going to be data I can perform math to. I can get the average favorite number, right? Temperature, the average temperature for a day, I can perform math to that, right? The amount of sales over the course of each month, right? I can perform math on that to get average sales or fluctuation or range. I can perform arithmetic, but any numbers or non-numbers, words, etc., if I can't perform math on it, it's going to be categorical data versus quantitative data. Qualitative data falls into that category of categorical data. Types of data also include time series and cross-sectional data. So cross-sectional data would be, if we had a number of people in one place at one time, if we had, how many people showed up to a concert, right? That's going to be just data from one observation. If I'm comparing it to how many people showed up for this weekly event this week versus last week versus the week before versus the week before, that's time series data. If I collect it over several time periods at regular intervals, then I can look for trends or make potential predictions or forecasts about the future in order to try to meet demand. You can see that kind of thing on a graph, the Dow Jones index values going up, going up, going up. Housing bubble crash of 2008, it all went down and then gradually built back up again. That's one example of time series data, looking for trends and observations. When you're gathering data and you're performing studies on the data, if you have a specific variable or thing you're looking to figure out, that would be experimental data. You have a theory about potential thing you want to start a study, you go in and you control for that. Non-experimental is just you're just gathering information to maybe make a forecast of the future, to make a recommendation of what to do later on. So here's data. There's no specific experiment at play, right? You're just looking at the survey results of how well customer service was at a restaurant, or what they liked about your menu or not. There's no experiment. We are not going into it thinking that we have this theory that the menu knowledge is going to be good from everyone. That wouldn't be the case here. We're just gathering data. Maybe we do something about that, and we prescribe some sort of recommendation on where we need to address our service for the consumers in the future, but we're not going into it with a specific theory. All right, distributions of data helps us figure out what's going on, to make predictions or to make recommendations to maybe fix something, but it allows us to learn from the data, to actually use it as usable information. So the first of that would be a frequency distribution. This is kind of like making a tally mark of every observation you've made to see how many people say that they prefer Coca-Cola to Pepsi to Sprite or some other soft drink, right? So here's an example of that. 50 soft drink purchases, and we're trying to see maybe how many people bought Coca-Cola, how many people bought Pepsi, Dr. Pepper, etc. This is categorical data. I can't do math on Diet Coke and Sprite, right? This is just data that gives us some information, but no arithmetic can be done on these specific words, right? So we look at a frequency distribution of those. How many people purchase Coca-Cola? 19 out of the 50. Now from there, we can look and say, okay, well, 19 out of 50 is 38%. So 38% of people prefer Coca-Cola. And then Pepsi was 13 out of 50. So that's 26%. And we can look at, maybe based on that, we can say, okay, well, when we do our next ordering to restock our shelves, maybe we don't need to get as much Sprite and Dr. Pepper as we are getting Pepsi and Coca-Cola. Those are the preferred soft drinks, right? So it does help us gather information. It does help us to use that information to make better decision making. But this is just a simple frequency chart. And here it is, where you can calculate it a slightly different way. These specific instances of observations are referred to as bins, typically BINS. So putting them in different bins. Imagine if you were taking up all the information, you grabbed one. Okay, Coca-Cola. I've got a little folder for that one. I put Coca-Cola in one. Diet Coke. Okay, I put that in one. So those are bins. That's why they're referred to as bins, because you're putting them in their separate categories and sorting them. Relative frequency. So this is, as I was just saying about percentages, finding a percentage. So we can tally all of the data up to see how many total observations there were, and then figure out what the percentage is. So here's what that table would look like with those 38%, 16%, etc. percentage of people who bought those types of sodas. And then from there, as I was saying, we could make those, we could use those to make better decisions as far as stocking our product in our supermarket. From here, we often will lay these out in a chart or graph of some kind by splitting them up into specific frequencies. To give relative information about them. What we'll do is say, there's an example. So this is the year-end audit times. How long did it take us to complete our audit at the end of the year? So this is the number of days, and these are the last 20 years of data of how long it took to perform our audit at the end of the year. Or maybe this is by department or something like that. So what we do is we look at all the observations of this that occurred, and then we look at the lowest point and the highest point, and we try to determine And I'll do the calculations as far as how we determined there was going to be 5 separate bins here on the other video, but we look at 5 points, 10, 11, 12, 13, 14 as our first bin. In the next 5 possible answers, 15, 16, 17, 18, 19 as our next bin. And from there, we count the number of observations that were in 10 to 14. So we can do this easily in Excel, but if you're doing it by hand, you would just do tally marks as you're going and say that, okay, so 4 of them were in the 10 to 14 days is how long it took us. And we can find out that the most frequent is going to be 15 to 19 days. From here, we add up that there was 20 total, and then 4 out of 20, or rather, sorry, not 20 total. Yeah, 20 total. So 4 out of 20 is 20%. 8 out of 20 is 40%. And we can see the percentage that falls into those bins. And that gives us maybe a better estimate of the expected amount of time it would take. There's only one time where it went 30 days or longer to complete the audit. So we wouldn't probably schedule for 30 days. We can look at the frequency, and it follows a chart where there's a high point that falls down from that high point, as it typically does, and say, well, it's probably going to take somewhere in the 15 to maybe 22 range is our 14 to 22 based on this, and maybe budget that amount of time. Like I was saying, it just helps you to make better decisions if the more information you have. A histogram is a way that these bins are typically presented. So you set up the whatever interest variable you have. In this specific instance, audit time in days. We do that on the horizontal or X axis, and then you end up with a chart like this, where basically in a histogram, these vertical bars are always butted up right to each other. You have a hard limit as far as what that number is, where it stops. So anything 10 to 14 is in this one. The line butts up right next to it. 15 to 19 is the next one. And there's always going to be some sort of high point. It's going to be typically centered around that high point somewhere, or not centered around it, but there's going to be a high point. Sometimes there's 2 that are tied. Those are, there's a specific name for them, which you'll discover a little bit later in the video. But this is what that would look like. We would take all the information, all of this, and we put it into a histogram. Skip the Excel part of it. I thought I took those out. You'll see that in the other video. This gives us a specific term, as I was saying, where that high point is either in the left side or right side, and that is skewness. We can see if the level of that tends to be on the left or right side of it. Skewed to the left would mean that the high point is on the right. And why that is that if the high point is over here on the right side of these bars, that means there's more data on the left side, which means more of it falls to the left of the mode of the most common one. So that's moderately skewed left. Moderately skewed right would be the opposite right here. Highly skewed right, meaning it's very high, and then everything else is very low, but there's a ton of it over there. There's even more observations. This is kind of a judgment call between moderately or highly skewed. Regardless whether it's moderate or high, it is skewed to the right if the high point is on the left, and vice versa. If the high point is on the right, it's skewed to the left. And I know as I'm holding this up, I'm mirrored, so it's probably not going left to right like what I'm saying, but look at this screen instead. So, and I just realized my laser pointer's not on. So yeah, high point on the right, then it skews to the left. High point on the left, it skews to the right. And then a symmetric skewness would mean that both sides are roughly equal, not maybe exactly equal, but pretty close as far as both sides of it. You've got the mode, or the more common one, in the middle of it, and then there's 3 observations on each side. Maybe the height of it isn't the same, but this would be symmetrical. This would be perfectly symmetrical, since it appears that they're both exactly the same on each side. And that's that. Cumulative frequency would be just the total number of everything. So very similar type of thing. Instead of writing it in a bin, 10 to 14, less than or equal to 14, right? So that there's 4 total. Less than or equal to 19. Well, that would include everything from 15 to 19, as well as everything that preceded it. So while there were 8 in that bin, if you rewind the video, there were 8 in that bin from 15 to 19. There's now 12 in the cumulative frequency. Cumulative means as you're going, you add it up. So 4 and 8 is 12, and then there's 5 more in this 20 to 24 range, which means everything less than or equal to 24, there's 17 total. So 4 plus 8 plus 5, okay? And then 2 and then 1. So you're just adding it up as you go. All right. Sometimes we want to locate a specific number within a series of numbers. The most common ones are going to be the mean, median, and mode. Mean, or arithmetic mean, is going to be the average. If you're talking about numbers, it's the average. To find the arithmetic mean, you would have add up all your numbers and then divide by the number of numbers. So if I add 5 numbers together, I get the sum of that, and I would divide by 5. If I'm adding 10, if I have 10 numbers, I'm going to find the average of. I add all 10 together, and then I divide by 10, and that gives me the average. So while there is, yes, Greek lettering on here, if you see this little symbol here that looks like a kind of a very sharp pointed E, that is the capital letter sigma. Yes, Greek letters do have capital and lowercase versions of them, but this capital letter sigma always means the sum of. This X would be a specific observation. So the sum of X1, I means you have a series of numbers. You don't know how many it's going to be. So the sum of X1 plus X2 plus X3, the second variable, the third variable, etc. And you just keep going until the end. And that n means whatever the end number of observations is. So if you see this, it means sum all of your variables together. I means just keep going to the end. Whatever that number of observations was, you divide by that number. So that's how you would interpret this. Add them all up, and then divide by however many there were you added together. If you wanted to find the average or mean of the sale price of a bunch of houses, you would add them all up and divide by, there were 12 observations, and you would get this. However, the problem with mean when it comes to something like this is that you might have one very high value, which messes it up and makes it seem higher than the rest. It'd be a perfect example of why mean or average isn't always the best example. If you had 10 people working in a place, and one of them made $10 an hour, and one made 11, and one made 12, and one made 13, and one made 14, and one made 15, and one made 16, and one made 17, and one made 18, and that last person made $200 an hour. The average pay for those workers would be pretty high because of that one person who made $200 an hour. Whatever that comes out to, I think it's, I've genuinely no idea what that comes out to, but let's say it was $40 an hour. Well, you have 9 people that make less than $20 an hour. Is the average pay $40 an hour? Yes, because of that person that made 200. But in that kind of instance, typically you'll see what's referred to as the median home value or the median salary for this thing, and that's because it takes it's likely to take out that skewness where somebody is kind of messing up the average, where it's not a reasonable number. You can't say the average pay is $40 an hour if 9 out of 10 people make less than $20 an hour, right? You could say it would be technically true, but it would be misleading. So instead, median is typically used, and how you find the median is you just line everything up in order, and whatever the middle number is, that's the median. So if I lined up all those salaries together, the median value would be something like 15, right? Which is probably a closer representation of how much people made per hour than whatever it was, 40 or. Now I want to do the math. I'll do the math in the other video. So the median is 46. If you have an even number of houses, for example, in this case, there were 12 houses and values. Anytime you have an odd number, you'll have a middle, right? Because there'll be an even number on each side of it. But if you have an even number of observations, you'll have 2 middle points. So you take the average of those 2 middle points. In this case, lining all these up, we get 199,500 and then 208,000. both in the middle. So that's 1, 2, 3, 4, 5 on this side of it, 1, 2, 3, 4, 5 on the other side. At that point, you just take the average of these two, you get a median value of 203,750. Mode just means which number happened the most. On that histogram, this would provide you that high point of a mode. So these 5 values. 46 happened 2 times. 2 happened more than any other observation. There was only 132, 142, 154, 246. So 46 is the mode. If more than one observation happened, the same amount, let's say you had 100 bits of information, and one number came up 5 times, and another number came up 5 times, and no other number came up more than 5 times, you'd have exactly 2 modes. You'd be a bimodal data in that set. If you had 3 or 4, or well, I take that back. 2 is also multimodal. So if it's at least 2, it's multimodal. But once you get to 3, 4, 5 or more, it's only multimodal. If it is exactly 2, it would be both bimodal and multimodal. It would be at least 2, but also exactly 2. When you're looking at growth rates, you would, instead of using an average, you would use what's called the geometric mean. There's a slightly longer formula for that, which you'll see in the other video. But basically, if you had a bunch of growth factors over time, you could multiply all these together and then take the nth root of the observation. So there's 10 observations. You multiply all these growth factors together and then take it to the 10th root of that. So, square root is the second root of something. Would mean that basically find a number where if you multiplied this number by itself 10 times, you'd get to this number. And there's, you can do this on some scientific calculators. Some you would need a more advanced calculator for this formula, like a TI-83. Or if you look online, there's root calculators. You can type in 10 as the root and then type in the number. It'll find the 10th root for you. But this tells us that the average growth would be 1.029, which is 2.9%. Slightly different way you do it when you're looking at growth factors. So that's that. Sometimes we want to measure the variability in something. There's various types of measurements at play. Here's an overview: range, variance, standard deviation, and coefficient. So from this, the range would be just the difference between the highest and the lowest value of something. If you want to know the range of house prices for sale, find the highest one and find the lowest one, subtract the lowest from the highest, and you could say the range is 348,250. If there is an extreme value, so there's one very high selling house in this neighborhood, you've got a mansion on the top of the hill, it's $1 million house, but most of the houses around it are $200,000, $300,000 houses, the range becomes quite high. And so that can badly influence it. So there are other ways of finding what we're looking for, where it's not as skewed, it's smoothed out a little bit more. One of those measures is in variance. So you find a standard deviation of the mean, and there's a lot of squaring of that information. Again, we'll get, this is more mathy, so we'll talk about this in the other video. But know that variance helps to try to smooth out that a little bit better than just taking the simple range where you take the high minus the low. You end up with something like this, where find the average, find how much each observation differed from the average. You square each of those, add them together, and then divide by the number of observations minus 1. Yeah, that'll make a little more sense when I'm going through it step by step. But just know that there's a formula for everything. You plug in numbers into a formula and you get the answer. So while this seems very intimidating and confusing and all of that, Once you learn the steps of it, you just plug in the same, follow the same steps every time with new values, and you come up with the answer. And with Excel, there's going to be a way to set this up where it always takes, specific values, and you can reuse the same template over and over again. It'll look something like that, but we'll get over into that in the other video. Square root of the variance is known as the standard deviation. It helps to further kind of figure out the distance of any one value from what the mean is and what to expect. Generally, a certain number of observations are within a certain number of standard deviations from the mean, and we will talk about that a little bit more when we are calculating it on the other video as well. But let's see here. Yeah, so we got 64 as the variance. The square root of 64 is 8. You end up with a 8 as your standard deviation. And yeah, we'll do that some more in the other video. All right, analyzing how data is distributed. You've got a few ways of doing that. Percentiles would be the first one. That's basically the approximate point where the data lies. If I wanted to know where 85 lied on a series of numbers, basically how well you did compared to all of the observations. Percentile is often used on standardized testing. Somebody scored in the 99th percentile. That means they scored higher than 98% of the people if you're the 99th percentile, I think. Yeah, so what percent do you have in the higher than X? If I wanted to know how many students scored at the 78th percentile or the 85th percentile, I could find that data. With that, we'll use those calculations on the other video. A quartile is, let's say I took all of the data and divided it into 4 equal parts. Each part would have approximately 25% of the observations in it, but not necessarily an equal spread as far as the values of those observations go. If I had, say 12 observations, there'd be approximately 3 of them in each of them. And then the quartile is the dividing line. So the quartile isn't the group of those, it's the dividing line. And we find out what the number is at each of those quartiles, so that the second quartile would be right in the middle. You have the first quartile, where 25% of them, the observations are in this zone. The second quartile would say that 25% of them are between the second and first quartile. So that second quartile number should be the median value. So that's what a quartile is. It's the dividing line where you divide the number of observations. You might have where the value of the observations is very high within one of the quartile. So 3 of the observations were in the above the third quartile, right? And so, but those were very high. So we can analyze that in different ways, but just to get the point across, the number of observations, not necessarily the value of observations. So you're not going to have averages and then divide those into quartiles. A z-score helps to find the relative location within a specific set of data. Again, it has interaction with the standard deviation value. There's a specific score that's associated with it. You'll see what's called a z-table, which is, I'm sure, in the index in the back of your book or within the chapter here. I'm not sure the exact location in the book. I will find that before I do the other video, but it's just used to find where that value is as it lies to the mean, whether it's to the left or the right of the mean. If it's to the right of the mean, it'll be a positive number, negative number if it's to the left of the mean. You'll see this calculation looks something like this. So each of these has a z-score that lies left or right of the mean. You've got the mean here, and then what standard deviation is to the left or right of that. That'll make a little more sense when we actually calculate it, I think, but that's the idea, is to assign a value to what that number of deviations away is. There's a rule in statistics and distributions, they call it the empirical rule, and basically that if the data follows a bell-shaped curve where it goes up and then back down, that once you figure out the standard deviation, about 68% of all the values will be within one standard deviation, either direction, positive or negative. 2 standard deviations should contain 95% of all the values, approximately 95%. And once you get to 3 standard deviations out, you're at about the 99% as far as all data values, which means there might be some that lay out outside of the 3 standard deviations, but that percentage is going to be less than 1% of all of them. And that rule just tends to always be there. That's why it's called the empirical rule, is because it's basically these calculations are set up in a way that it will contain that. It would have to be a very severe outlier to be outside of that, and that's what's listed here. Extreme values in a data set are outliers. So anything where the z-score of it is further to the left or further to the right of 3 standard deviations, that would be an outlier. A box plot is just a type of graphical representation of this, of where the quartiles are of a value, and finding that within finding those outliers within this visualization. We'll go over the calculations of this to try to make this make a little bit more sense. They call this a box and whisker chart. These whiskers are drawn from the ends of the box, where the smallest and largest values are within a certain range of the quartiles. I don't want to go too far into this, but just know that a box plot is a graphical summary based on the quartiles of a data set. Is how you would find that. Here's another one, type of box plot. Home sales in various communities. So the Fairview home sales versus Shadyside and all these different neighborhoods. All right. How could we read this information? We would see that Shadyside and Shadyside has the highest value because all of these plots are within this box, and it's the highest value. Hamilton would be the lowest median house sales within there, and then when you have a spot outside of that, you've got outliers in Irvington, where this one spot in Irvington is an outlier because it lies, more than 3 standard deviations away, but we'll create a box plot in the next video. All right, measuring the association between 2 variables is our next and I believe final section. You've got scatter plots. This is where you can try to figure out the relationship between 2 variables, and then covariance is to try to figure out what that association means. Can we find a specific value and help us to do forecasting with it? So what 2 variables might we use? Well, how high is the temperature outside, and how much bottled water do we sell with that specific temperature? All right. Well, if we put temperature, this could go either way, but let's say we went temperature on the x-axis and bottled water on the y-axis, then I could make one dot where 78 and 23 intercept. So that's what a scatter plot is. I'd look at 78 on the X and 23 on the Y, and where those 2 things meet, I put a dot. And I keep doing that for all of these, and what you end up with is a scatter plot like this. And if you look, you could make the conclusion that it certainly appears that as the temperature goes up, the number of sales of bottle of water goes up. from 23 up to 30 or so. So from that, we can figure out potentially what the correlation coefficient of temperature and sales is, such to the degree that we could say, well, we could figure out what the likelihood of how much we're going to sell at 85 degrees is, or 86 or 89, and we could figure out a forecast for, if we knew the temperature, how many bottles of water do we need to put in the fridge that day or something like that. So there's a calculation for this that's a lot easier than it appears on this, but we'll go over that in the other video. But that's what the idea is. A scatter plot would show us the relationship, and then the covariance would be a specific value, or rather, is there a positive relationship between them? And we find a covariance of 12.8. That number is above 0, so there's a positive relationship. If that number was below 0, there'd be a negative relationship. A negative relationship would say that as the temperature goes down, as one goes down, the other goes up. So that's a negative relationship. One goes down, the other goes up. If one goes up and the other goes up, that's a positive relationship. Negative and positive, when it comes to statistics, don't necessarily mean there is one or there isn't one. You might think negative relationship is there's no relationship, or there's less than no relationship between these two things. But that's not what it means. It means that as one goes up, the other goes down, or vice versa, that they have opposite effects on each other. There can still be a very strong relationship between them. It's just when one goes up and the other goes up, that's a positive relationship. We can find a specific coefficient, and the coefficient gets multiplied by another value and helps us to determine the forecasting of something. When you're interpreting it, if it's near 0, there's probably not a relationship. So as this number gets closer to 0, the likelihood of a relationship between those numbers goes down. If the number is less than 0, and it can go all the way up to -1, 1 being -100%, that's the lowest it can go, and then +1 being 100% positive relationship. It's more or less percentage of how much that relationship exists and whether it's a negative or positive relationship. So on a graph, if it was a positive relationship, you can see as one goes up over time, the other goes up. As one goes up over time, the other goes down. So as it goes further along the x-axis, this value is going down. They're negatively linearly related, positively linearly related. But here, basically, there's no trend up or down either direction. So when we do the calculation on this, it's probably going to be close to 0, because this is completely random on the scatter plot. We do all of this, and we can say we get that's very high. That's a very high positive relationship between these. As the temperature is going up, there's a very strong linear relationship. So as the temperature goes up, sales are going up. And then the final example is going to be where there's a non-linear relationship with a near 0 correlation coefficient. So this is an interesting example wherein how much do you spend on environmental control? Well, if the temperature is very cold, you spend a lot because you're spending it on gas. If the temperature is very hot, you're spending a lot because you're spending it on central air conditioning. But if the temperature is in this range, you're not spending as much because the temperature is, just right. You're not needing to heat the house as much. You're not needing to cool the house as much. So that can also happen as well. All right. A little bit longer of a video than I expected, but a lot to cover and recap in this chapter. So we'll see you in the quantitative video separately, which will help you get your problem set done this week. Thanks, everybody. I'll see you in the next one.